Okay, we've now looked at charges, electrostatics. Remember we looked at the forces on the charges due to the positives, the negatives, etc., etc. How many electrons even were involved in that. Now we're going to look at the flowing of the charges. We're going to look at electric circuits, okay? We're going to pull it all together right at the end of this, where we look at electrodynamics, is the moving of the machinery, the motors, the generators, how we generate current in our houses, AC, DC, and batteries. We're going to look at all of that. It's even going to come together in grade 12 in chemistry, where we actually do the whole battery. What is a battery? How does it work? And we look at the half reactions of batteries and things like that. So we're all pushing now towards the grand finale of putting the physics and the chemistry all together in the real world. You know, for those of you going on with the sciences to the engineerings or nuclear physics or maths or wherever you're going to go, these are the kind of things. It's really a way of thinking that they're after. The problem solving plays a huge role in it. But now let's have a look at the electric circuit. Remember, from last year and just general, we've got a few things we can put in a circuit. We've got a battery that we can put in a circuit. We can put light bulbs in a circuit. We can put resistors in a circuit. We're not going to do capacitances, inductors, and things like that, but they all get put into the circuit. Transistors get put into the circuits and things like that. Today we've got the microchips in the circuit, but they are all components that fit into an electric circuit. Probably, I guess, one of the most amazing things in life that we have essentially is the electric circuits. We live with them daily. It's in everything we do. Somebody said to me that the amount of computing power in today's washing machines is the same as was put into what they used to put somebody on the moon. I don't know if that's true or false, but you know, it shows where we've come from. It doesn't show where we're going to, but I'm sure there's going to be huge advances in electronics, as there is every month. If you look at it, the products that get launched, the things they can do, and also the whole drive towards making things smaller, the nanotechnology kinds of approaches. But let's look at a circuit, right? Now, what do we have to remember first about a circuit? Well, the very first thing is that we only in the circuit have three elements. We have a voltage, V. We have a current, I, in amps. We have resistance, R. Those are the only three things we've got. There's nothing more we have to work with. Now, also bear in mind that at the end on the schedule, these are given to you, the formulas that you have to have. So what do we have to recognize? We have to recognize that the elements that go into a circuit, our resistors, can be put in different ways. So just like if you think about it, you've put batteries into a torch, all right? And you come along and you put your batteries one behind each other, generally speaking, don't we? So let us start with that basic premise there of putting one behind the other, right? There's a battery. And what do? We put another battery there, like so. We put another battery there, like so, right? And on each of those batteries, it says 1.5 volts. Let's say, on the batteries. What have we got? Diagrammatically, we've got each one of those is a cell, all right? And each one is 1.5 volts, isn't it? So what have we got overall there? We've got a total of 1.5, 3. We've got 4.5 volts, right? There we've got a battery of 4.5 volts made up of 3 cells. Okay. Now they are placed one behind each other, which means that they are placed in series. Okay? They are placed in series. Now, let's think about it this way. we're putting one behind the other one. So we're lining them up. So actually what are we doing? We are increasing something, right? We are increasing the voltage because we're pushing one behind the other. Okay, it's like a whole bunch of shells or bullets all lined up behind. We're increasing the heating power of those, right? They are in series. Now, just a silly little thing, just a little bit of recapping. Obviously, we could have put a battery in the wrong way around of 1.5 volts that way. What are we actually doing? We are then taking a cell effectively and cancelling it out onto it. Because these volts here, and I know this is not technically true, but they are all pointing that way. This one is pointing that way, which means that's going to cancel with that, and we're going to then be left with 3 volts at the end of the day. Okay, that's just a little bit of a recap. Just watch. I haven't seen it in any of the problems you get, but it could come up, you never know. All right. Similarly, we could have done this, and you do see it, you definitely see it. We can be putting our batteries like this, can't we? Which, if I diagrammatically represent it, it's like that, correct? And we go down there, and we go down there like that. Now we've got 1.5 here, 1.5, and 1.5. You can see what's happened here, right? This is in parallel. Because that one is parallel to that one, you can see they are parallel to each other with a wire joining each one from the back. The voltage of all of this lot, though, the voltage there is 1.5 volts, right? It can't be more because we've only got one there, and when that's done, then the next one, then the next one, we've only got 1.5 volts. Okay. Different reasons for connecting things in different ways. We'll get to that. So now, similarly, then all we have to say is we say, all right, I can then say a resistor. What is a resistor? A resistor is an element. Oh, a resistor, great one. A light bulb, right? You've seen if you look inside a light bulb, if you have a look, you'll see the thing coming up, and you'll see a very thin, like little coil sometimes, or a very thin little strand of metal going across between the two terminals like that, right? So it looks a little bit, if I look on the inside, like that, okay? And we've got this very, very thin little element going there. What is happening? The current's coming up here and going down there. It's going through there. If we exaggerate it, what have we got? That there is a tube this size, right? And we've got all our electrons, or water. Think of electricity and water, same. We've got all our electrons piling down there, and all of a sudden they come to this little hole over there, right? So what are we doing? It's the same thing as you've got this huge crowd of people, and you funnel them down into a tiny little space, right? What happens? The space between everybody gets less and less and less. As the space between the people gets less and less, the temper of the people starts rising and rising and rising, doesn't it? It starts to get warm because of all the bodies packed together, but it gets extra warm because everybody's getting a little bit ticked off by having to be pushed into this tiny little space because they don't want to be in each other's personal space. They don't like it. Do people like being crammed together in a train? No, we don't. Guess what? Electrons, which is the flow of current, isn't it? They don't like it either. Okay? There's a human property of an electron for you. So they don't like being crammed in. So you start getting heat given off over here, right? The heat of irritation at being stuck in this confined space. That heat causes this little thing to glow, doesn't it? This element here, this constriction of flow, is our resistance. This essentially is our resistor, right? It could be made of different materials or whatever the case might be, but it's a resistor. if you think of it as a hose pipe, you turn the tap on and the water flows out the end. If you start squeezing it, what are you doing? You are increasing the resistance to flow of the water out of the pipe. Therefore, you get less volume. Granted, the pressure goes up, all right? That's a byproduct of doing it. But similarly, if we push here, all right, on our thing, we slow it down. So the resistors are slowing it down, all right? And because we're doing that, yes, let's say the pressure goes up. The pressure goes up. That's why we're getting the heat out of a resistor, right? Now, resistors can also be placed in a circuit. I know a bit of this is revision, so we'll just move through it just for revision's sake. Right. What have we got here? Same as the batteries, one alongside each other. So this is a series connection. These three are in parallel with each other, right? Therefore, they are parallel connectors, right? And if you remember, there was the formula for calculating them. Let's just recap the formula for calculating them. What are we doing? We actually want to break any circuit down, okay? We want to break it down into the bare bones circuit of it all. And what is the simplest possible circuit we can have? It is a simple or single power source with a single resistor R. I'm putting in an ammeter there, I'm putting in a voltmeter there, and I'm going to put a voltmeter in over there, right? Now, that's the simplest circuit. So we try and reduce everything down to that. That's what we're after, right? How do we do it? Well, there's the formula for it, isn't it? We are going to pretend to take away the resistors in series, and we're going to put in what we call an effective resistor. So we're going to replace these three resistors of ours over here, right? Let's just go back to that. We're going to replace those three resistors there with an effective resistor, which is just one, right? How do we do that? Well, it's actually the same as the batteries. We would say R effective is going to be R1 plus R2 plus R3, which means we've got, if we just roll it down slightly, we've got here, this is R1, this is R2, and this is R3, right? So what do? We take the sum of the resistors, all right, in series and add them together. It doesn't matter where they are in the circuit, by the way. They could be one down this side, one along here, and two up that side. They are all essentially in series, right? Now, the next thing is then to say, okay, what if we've got resistors in parallel in our circuit? What do we do then? Well, we do the same thing, and you remember, let me just write on that one there. Let's do it in blue, shall we? Okay, so we've got, this is now R1, this is R2, this is R3. What do I want to do? I want to replace all of those with one resistor over there called R effective, right? In other words, it's, if I cut those three out, I can replace it with just that one, right? Let's see what the formula for that one is. It is 1 over R effective is 1 over R1 plus 1 over R2 plus 1 over R3. Okay? Simple as that. Just as an aside, I was asked yesterday actually, but what if you've got something that looks like this? If you've got a resistor here and a resistor here, and then for example, We've got another resistor over there and a resistor here. And let's say we've got a resistor over there. All right. Now, what is the effective resistance of this? Let's call this 2, 3, 5, and 2 maybe. Let's call this 2 and 4. Okay, and just try and keep even numbers here, just for the heck of it. And this one, let's call this one 10. All ohms, of course, so let me put in my units correctly. Right, 10 ohms like that. What is it? What do we do? Well, the first thing we do is we go and we see over here, right? I could draw that like this, couldn't I? Right? It would be the same, wouldn't it? If I'm looking at the how to connect it, I just have a little bit extra wire up and down over there. So first of all, I can look at it like that. So I need to break it down bit by bit to work with it to get one single resistor. So how do I do it? Well, first of all, I say these two, this number 1 and number 2 here, they are in series, aren't they? So I add them. So then I'm going to break it down to say, right, guys, I am going to make you look like this. There's one resistor going in over here, which is going to take you guys. And that resistor is going to be a 6 ohm. Correct? Right. If you just bear with me, I just want to change that to a 3. Okay. I was trying to keep it to be even. Then I'm going to say, okay, what do I do next? I say, right, these two are connected over there. So there we go. All right. That is now an 8 ohm resistor, isn't it? I add those together because they're in series, which gives me an 8 ohm resistor. Now I've got those two in parallel, right? Because I've got to keep breaking it down until I've got one resistor left. In other words, I can take all the others out and replace it with that one. Now I have to use the formula. 1 over R effective is going to be equal to 1 over, in fact, I've been asked by the producers to use as much color as possible and not overlap. So let's have a look. Now I say 1 over R effective. I'm looking for that guy, aren't I? The one I can replace these two with. Cut those out. That one's replaced those, right? Let's just get this down because it's important. That one's replaced those. The two blue ones here, that's been replaced there, right, by the 8. We just added them. Now I'm trying to get the green one, right? The green one is 1 over R effective, is going to be 1 over 6 plus 1 over 8. And then we work out 1 over R effective is going to be, I'm just going to use my calculator for this. Okay, so we've got here 1 over 6 equals that, plus 1 divided by 8 equals that. That's going to be 129 over 8. But now don't forget, please don't do these calcs in your head and try and automatically flip. The chances of making an error here. Remember, what are we about? What we're trying to do is we're trying to get recipes and simplify this as much as possible. At the end of the day, though, in following the recipe, don't shortcut it. Write it down and then flip it at the end. After all, why would you want to go through all of this and just because of a silly mistake, you end up getting 0? So let's flip it. So then we say that therefore, I can replace you all with to the minus 1 equals that 8 over 129. Okay, 8 over 129 is going to be that guy, and that's going to be 0.06. I want to recheck that because that just looks not right. Okay, let me just check. Sorry guys, 1 divided by 6 is equal to that. Okay, plus 1 divided by 8 equals that. My bad. I think I pushed minus. My apologies. It just didn't look right. Okay, so what have we got? It's 7 over 24. Let's flip it. It's 24 over 7. Okay, to the minus 1 equals that. And SD 3.43. Okay, 3.43 ohms. So what have we got? We've got a 3.43. This is now 3.43 ohms over there. So what's my total resistance in the circuit? My total resistance in the circuit, I just now need to add this one, don't I? 10. So my R for my circuit is equal to 13.43 ohms, right? So that's section 1. Those are what we do. We break it down until we've got down to one resistor, one power source, i.e. the battery, and remembering we've only got V, I, and R. Why do we bring it down to 1? So that we can start solving the circuit. Where do we start in any physics problem, any maths problem, any chemistry problem? Generally any problem worldwide where we've got the most information, and we work out from that. Even if you think about normal problems, economics, business studies, you start where you're given the most information, work out from that, right? So we've now got that. The next one, I'm going to look at bringing it down to a circuit, and then we're going to solve for the current. Then we're going to move on, we're going to introduce some circuits and start solving for the circuit, right? And at the end, we're going to bring in the internal resistance of the battery, which is something that very often gets neglected. And last of all in this series, we're going to be looking at the power dissipated, which means the heat given off by resistors, power in circuits and things like that.